The Islamic Golden Age, spanning from the 8th to the 14th century, was a period of remarkable intellectual and cultural flourishing in the Islamic world. During this era, scholars made significant advancements in various fields, including mathematics, medicine, philosophy, and notably astronomy. The Islamic Golden Age saw the rise of great cities like Baghdad, Cairo, and Cordoba, which became centers of learning and innovation. It was a time when knowledge from different cultures was eagerly sought, preserved, and expanded upon. Astronomy held a special place during the Islamic Golden Age. Islamic scholars were deeply motivated to study the heavens for both practical and religious reasons. One of the primary motivations was the need to accurately determine the direction of Mecca for prayer, as well as to establish the Islamic lunar calendar. This practical necessity drove astronomers to develop sophisticated methods for observing and calculating celestial movements. Islamic astronomers made significant contributions to the field, such as refining the Astrolabe, developing new astronomical tables, and making precise observations of celestial bodies. These advancements were not just theoretical, but had practical applications in navigation, timekeeping, and agriculture. The establishment of observatories in cities like Baghdad and Samarkand further propelled the study of astronomy. The importance of astronomy during this period cannot be overstated. It was a field that bridged the gap between science and religion, practicality and theory. The meticulous work of Islamic astronomers laid the groundwork for future discoveries and had a lasting impact on scientific community. Their contributions are a testament to the Islamic Golden Age's enduring legacy in the history of astronomy. During the Islamic Golden Age, one of the most remarkable achievements was the preservation and translation of ancient Greek texts. This period saw an unprecedented commitment to the collection, translation, and dissemination of knowledge from diverse cultures. The Islamic world became a melting pot of intellectual pursuits, where scholars actively sought to preserve and expand upon the works of earlier civilizations. The translation movement began under the Abbasid Caliphate, particularly during the reign of Caliph Harun al-Rashid and his son, Caliph Al-Mamun. Al-Mamun established the Bait al-Hikmah, or House of Wisdom, in Baghdad around the 9th century. This institution served as a major center of learning and translation, attracting scholars from various parts of the Islamic world and beyond. The House of Wisdom became a hub for translating Greek, Persian, Indian, and other texts into Arabic. The preservation of Greek astronomical texts was of particular importance to Islamic scholars. They recognized the immense value of the works of renowned Greek astronomers such as Ptolemy, Aristotle, and Hipparchus. These texts contain detailed observations, calculations, and theories that form the foundation of classical astronomy. By translating these works into Arabic, Islamic scholars ensured that this invaluable knowledge was not lost to the ravages of time. The translation process was meticulous and required a deep understanding of both the source and the target language. Scholars like Hunayn ibn Ishaq and Thabit ibn Qurra played pivotal roles in this endeavor. Hunayn ibn Ishaq, a renowned translator, translated numerous Greek texts, including Ptolemy's Almagest, into Arabic. Thabit ibn Qurra, another prominent figure, not only translated but also critically examined and expanded upon the Greek works. One of the significant contributions of Islamic scholars was their approach to translating these texts. They did not merely translate word for word. Instead, they engaged with the material, critically analyzed it, and often made improvements and corrections. This rigorous approach led to the development of new ideas and the refinement of existing theories. The translations were not static but dynamic, reflecting the active intellectual engagement of Islamic scholars with the ancient knowledge. The impact of this translation movement extended beyond the Islamic world. The translated works were eventually transmitted to Europe, where they played a crucial role in the Renaissance and the scientific revolution. European scholars such as Gerard of Cremona translated the Arabic versions of Greek texts into Latin, making them accessible to a wider audience. The preservation and dissemination of Greek astronomical knowledge by Islamic scholars thus bridged the gap between the ancient and the modern world. In addition to preserving Greek texts, Islamic scholars made their own significant contributions to astronomy. They built upon the foundations laid by the Greeks and developed new astronomical models, improved instruments, and more accurate observations. The integration of Greek knowledge with Islamic innovation created a rich tapestry of astronomical understanding that would influence generations to come. The preservation and translation of Greek texts during the Islamic Golden Age exemplified the dedication of Islamic scholars to the pursuit of knowledge. Their efforts not only safeguarded the intellectual heritage of ancient civilizations, but also paved the way for future advancements in science and astronomy. This remarkable period of intellectual cross-pollination underscores the importance of cultural exchange and the enduring legacy of the Islamic Golden Age in the history of human knowledge. During the Islamic Golden Age, one of the key factors that propelled astronomical studies to the new heights was the development and refinement of astronomical instruments. Islamic astronomers were not only scholars, but also skilled craftsmen who created and improved devices that allowed for more precise observations of the heavens. One of the most significant advancements was in the design and use of Astrolabe. The Astrolabe, an ancient Greek innovation, was vastly improved by Islamic scholars. It became a multifunctional instrument used for solving problems related to timekeeping, navigation, and the measurement of celestial objects. With its intricate design, the Astrolabe allowed astronomers to measure the altitude of stars above the horizon, determine the time of day or night, and even find the direction of Mecca for prayer. Scholars like Al-Fazari and Al-Battani made substantial contributions to the development of more advanced and accurate astrolabes. Another pivotal instrument that saw advancements during this period was the quadrant. The quadrant was a quarter-circle panel used to measure the altitude of celestial objects. Islamic astronomers improved its design, making it more precise and easier to use. This instrument was crucial for astronomical observations and navigation, allowing for more accurate measurements of the positions of stars and planets. The armillary sphere was yet another instrument that Islamic astronomers refined. This model of celestial sphere, consisting of a series of rings representing the great circles of the heavens, was used to demonstrate the apparent motions of stars around the Earth. Islamic scholars like Al-Farghani and Al-Sufi enhanced the armillary sphere, making it a vital tool for teaching and understanding celestial mechanics. Islamic astronomers also made strides in the construction and use of observatories. Observatories in cities like Baghdad and Samarkand were equipped with state-of-the-art instruments and served as centers for astronomical research and education. These observatories provided a dedicated space for systematic observations and the recordings of celestial phenomena. The Marogeh Observatory, founded by Nasir al-Din al-Tusi in the 13th century, is one notable example. It housed an impressive array of instruments, including a large wall quadrant and an armillary sphere, enabling astronomers to make precise measurements and calculations. One innovative instrument developed during this period was the sextant, an early version of which was used by Islamic astronomers to measure the angular distances between celestial objects. The sextant's design evolved over time, eventually becoming a crucial tool for navigation and astronomy. In addition to these instruments, Islamic astronomers also made advancements in the production of astronomical tables, known as zich. These tables contained comprehensive data on the positions of celestial bodies, solar and lunar eclipses, and other astronomical phenomena. The advancements in astronomical instruments during the Islamic Golden Age were instrumental in expanding our understanding of the cosmos. These tools enabled Islamic scholars to make more accurate observations, develop new theories, and refine existing knowledge. The legacy of these innovations continues to influence modern astronomy, highlighting the enduring impact on the field. In the rich tapestry of the Islamic Golden Age, Al-Fazari stands out as a pivotal figure in the field of astronomy. His work not only advanced the understanding of celestial phenomena, but also laid the groundwork for future scholars. Al-Fazari, whose full name was Muhammad ibn Ibrahim al-Fazari, was a Persian scholar who lived in the 8th century. He is often celebrated as one of the earliest Islamic astronomers and mathematicians, and his contributions to the field have left an enduring legacy. Al-Fazari's interest in astronomy was deeply intertwined with his work in mathematics. He understood that precise mathematical calculations were essential for accurate astronomical observations. One of his significant contributions was his role in translating and enhancing the knowledge inherited from previous civilizations. Al-Fazari translated important Greek and Indian astronomical texts into Arabic, making this knowledge accessible to the Islamic world. His translations played a crucial role in preserving and disseminating the astronomical wisdom of ancient cultures. Among his notable works is his translation of the Sindhin, an astronomical text of Indian origin. This text, originally known as the Siddhanta, was a comprehensive treatise on astronomy and mathematics. Al-Fazari's translation, along with his commentary and enhancements, introduced sophisticated astronomical concepts to the Islamic world. The Sindhind provided detailed information on planetary movements, lunar and solar eclipses, and other celestial phenomena. Al-Fazari's work on this text demonstrated his deep understanding of both the theoretical and practical aspects of astronomy. Al-Fazari's contributions extended beyond translations. He was also an innovator who developed new instruments and methods for astronomical observations. One of his significant achievements was his work on the Astrolabe. While the Astrolabe was an ancient Greek innovation, Al-Fazari refined and improved its design, making it more accurate and versatile. His enhancements allowed astronomers to measure the altitude of celestial bodies more precisely and facilitated various calculations related to timekeeping and navigation. In addition to his work on Astrolabe, Al-Fazari was instrumental in the development of armillary sphere, another critical astronomical instrument. The armillary sphere, with its series of rings representing the celestial circles, was used to model the apparent movements of stars and planets. Al-Fazari's improvements to the armillary sphere made it a more effective tool for teaching and understanding the mechanics of the heavens. Al-Fazari's influence extended to his role as a teacher and mentor. He was part of the intellectual circle that flourished under the patronage of Abbasid Caliphate. His teachings inspired a generation of scholars who would go on to make their own significant contributions to astronomy and other sciences. Al-Fazari's legacy can be seen in the work of later astronomers like Al-Battani, who build upon the foundations laid by their predecessors. One of the hallmarks of Al-Fazari's approach to astronomy was his emphasis on empirical observation and mathematical precision. He believed that accurate data collection and rigorous calculations were essential for understanding the cosmos. This approach was a departure from the more speculative and philosophical methods of earlier astronomers and set a standard for scientific inquiry that would influence future generations. Al-Fazari's contributions to astronomy during the Islamic Golden Age were instrumental in advancing the field and bridging the gap between the ancient knowledge and the new discoveries. His work exemplifies the spirit of intellectual curiosity and innovation that defined this remarkable period. Through his translations, instrument development, and mentorship, Al-Fazari left an indelible mark on the history of astronomy, ensuring that knowledge of the heavens would continue to evolve and inspire future generations. Al-Battani, also known as Al-Battanius in the Latin world, was a renowned Islamic astronomer and mathematician who lived during the late 9th century and early 10th century. His full name was Abu Abdallah Muhammad ibn Jabir ibn Sinan al-Raqi al-Harani al-Sabi al-Battani. Born in Haran, a city in what is now southeastern Turkey, Al-Battani made significant contributions to the field of astronomy that have had a lasting impact on the scientific community. One of Al-Battani's most notable achievements was his improvement of Ptolemaic astronomy. He critically analyzed Ptolemy's work, particularly the Almagest, and corrected several of his errors. Al-Battani's observations and calculations were remarkably precise for his time, and he made significant advancements in understanding the movements of celestial bodies. His work included the measurement of the length of the solar year, which he calculated to be 365 days, 5 hours, 46 minutes and 24 seconds, a value that is remarkably close to the modern measurement. Al-Battani's most famous work, the Kitab al-Zij, also known as the Sabian Tables or the Book of Tables, was a comprehensive astronomical treatise. In this work, he compiled extensive astronomical data, including the position of stars and planets, as well as tables for calculating the positions of celestial bodies. The Kitab al-Zij became a highly influential text, widely used by astronomers in both the Islamic world and Europe. It provided a more accurate and detailed understanding of the heavens, serving as a valuable resource for future generations of astronomers. Another significant contribution of Al-Battani was his work in trigonometry, which played a crucial role in advancing astronomical calculations. He introduced the use of sine and tangent functions, replacing the previously used by Greek chord method. Al-Battani's development of trigonometric functions allowed for more precise and efficient calculations of celestial positions. His work in this area laid the groundwork for the development of modern trigonometry and its applications in various scientific fields. Al-Battani's contributions extended to the observation and prediction of lunar and solar eclipses. He meticulously recorded the timings and positions of eclipses, providing valuable data for future astronomers. His accurate predictions of eclipses demonstrated his deep understanding of celestial mechanics and his ability ability to apply mathematical principles to astronomical phenomena. In addition to his observational and theoretical work, Al-Battani made significant improvements to astronomical instruments. He refined the design of Astrolabe, making it more accurate and versatile. His enhancements allowed astronomers to measure the altitude of celestial bodies with greater precision, aiding in navigation and timekeeping. Al-Battani also worked on the development of sundials and other timekeeping devices, contributing to the accurate measurement of time based on the position of the sun. Al-Battani's influence extended beyond his lifetime. As his works were translated into Latin and studied by European scholars during the Renaissance, his Kitab az-Zij was translated by Gerard of Cremona and became a standard reference for astronomers in medieval Europe. The accuracy and comprehensiveness of Al-Battani's data made his work a cornerstone of astronomical studies, bridging the gap between ancient Greek astronomy and the scientific advancements of the Renaissance. The legacy of Al-Battani is a testament to the intellectual rigor and innovative spirit of the Islamic Golden Age. His contributions to astronomy, trigonometry, and the development of astronomical instruments have had a profound and lasting impact on the field. Al-Battani's work exemplifies the synthesis of observation, mathematical precision, and critical analysis that characterize the scientific achievements of this remarkable period. His enduring influence continues to inspire and inform the study of the cosmos today. Al-Khwarizmi, often hailed as the father of algebra, was a pioneering Islamic scholar whose contributions during the Islamic Golden Age extended far beyond mathematics. His full name was Muhammad ibn Musa al-Khwarizmi, and he lived during the 9th century, primarily in Baghdad. Al-Khwarizmi's work in mathematics, astronomy, and geography had a profound impact on the intellectual landscape of his time and laid the groundwork for many future advancements. Al-Khwarizmi's interest in astronomy was closely linked to his mathematical pursuit. He understood that accurate astronomical observations required precise mathematical calculations. One of his most significant contributions was the development of trigonometric tables that were essential for astronomical calculations. These tables included values for sine and tangent functions, which allowed astronomers to make more accurate predictions of celestial events and positions of stars and planets. Al-Khwarizmi's work in trigonometry laid the foundation for future astronomers and mathematicians to build upon. In addition to his work on trigonometric tables, Al-Khwarizmi made substantial contributions to the field of astronomical geography. He authored a comprehensive work titled Kitab Surat al-Ard, the book of the description of the Earth, which provided detailed information about the geographical locations of various cities and regions. This work was based on the Ptolemaic model but included corrections and updates based on more accurate observations. Al-Khwarizmi's geographical work was instrumental in improving the accuracy of maps and understanding the spatial relationships between different regions. One of Al-Khwarizmi's most notable achievements in astronomy was his work on the Zij al-Sindind, an astronomical treatise that provided extensive tables and calculations for predicting the positions of celestial bodies. This work was based on Indian astronomical knowledge and was one of the earliest and most influential Zij produced in the Islamic world. The Zij al-Sindind included data on the movements of the sun, moon, and the planets, as well as calculations for determining the times of lunar and solar eclipses. Al-Khwarizmi's meticulous work on these tables set a high standard for future astronomers and was widely used for centuries. Al-Khwarizmi's contributions to astronomy were not limited to theoretical work. He also made significant advancements in the development of astronomical instruments. He improved the design of the Astrolabe, an ancient Greek instrument used for measuring the altitude of celestial bodies and solving problems related to timekeeping and navigation. Al-Khwarizmi's enhancements to Astrolabe made it more accurate, versatile, allowing astronomers to perform a wider range of calculations with much greater precision. Another important aspect of Al-Khwarizmi's work was his role in the translation and preservation of ancient knowledge. He was part of the House of Wisdom in Baghdad, an intellectual center where scholars translated and expanded upon the works of earlier civilizations. Al-Khwarizmi translated Greek and Indian astronomical texts into Arabic, making this knowledge accessible to the Islamic world. His translations and commentaries enriched the intellectual heritage of the time and ensured that valuable astronomical knowledge was preserved for future generations. Al-Khwarizmi's legacy in astronomy is a testament to his dedication to the pursuit of knowledge and his ability to integrate mathematical precision with empirical observation. His contributions laid the groundwork for many of the advancements in astronomy during the Islamic Golden Age and had a lasting impact on the field. The influence of his work can be seen in the development of later astronomers, both in the Islamic world and in Europe, where his works were translated and studied during the Renaissance. The Islamic Golden Age was marked by numerous significant advancements in the field of astronomy. Islamic astronomers made groundbreaking discoveries and developed innovative theories that profoundly impacted our understanding of the cosmos. Their meticulous observations, mathematical precision, and critical analysis led to major astronomical achievements that continue to influence modern science. One of the most notable achievements during this period was the refinement of the Ptolemaic model of the universe. The Ptolemaic model, which described the geocentric arrangement of celestial bodies, was the dominant astronomical framework inherited from the Greeks. Islamic astronomers such as Al-Battani and Ibn al-Shatir critically examined and improved upon this model. Al-Battani's precise measurements of the solar year and the orbits of planets led to the corrections in Ptolemy's calculations, making the model more accurate. Ibn al-Shatir further refined the Ptolemaic system by introducing the concept of secondary epicycles, which provided a better explanation of the observed planetary motions. Another major achievement was the development of accurate astronomical tables known as zich. These tables contained comprehensive data on the positions of celestial bodies, lunar and solar eclipses, and other astronomical phenomena. The zich compiled by Al-Battani, known as the Al-Battani tables, and the Toledian tables, created by Al-Zarqali, were among the most influential. These tables were used by astronomers for centuries and played a crucial role in advancing our understanding of celestial mechanics. Islamic astronomers also made significant contributions to the study of lunar and solar eclipses. They developed methods for predicting the timings and positions of eclipses with remarkable accuracy. Al-Biruni, for example, provided detailed descriptions of both lunar and solar eclipses, including the conditions under which they occur. His work in this area helped improve the accuracy of eclipse predictions and provided valuable data for future astronomers. The study of planetary motion was another area where Islamic astronomers excelled. They developed sophisticated models to describe the movements of planets and their orbits. Al-Tusi, a prominent astronomer, introduced the Tusi Couple, a geometric model that explained the apparent motion of planets without relying on the Ptolemaic epicycles. This innovative model was later used by Copernicus in developing the heliocentric theory of the solar system. The Islamic Golden Age also saw the establishment of the observatories, which played a critical role in advancing astronomical research. The Marogeh Observatory was one of the most famous. Equipped with the state-of-art instruments, the observatory provided a dedicated space for systematic observations and the recording of celestial phenomena. The observatory's staff compiled extensive astronomical data, which contributed to the development of more accurate models of the universe. Islamic astronomers made significant advancements in the development of astronomical instruments as well. They refined the design of the Astrolabe, making it more accurate and versatile. The Astrolabe was used for various purposes, including measuring the altitude of celestial bodies, determining the time of day or night, and finding the direction of Mecca for prayer. Islamic scholars also improved the design of quadrants, sextants, and armillary spheres, enhancing their precision and utility in astronomical observations. In addition to these achievements, Islamic astronomers made important contributions to the field of timekeeping. They developed sophisticated methods for measuring time based on the position of celestial bodies. Al-Biruni's work on the determination of Earth's radius and circumference, as well as his development of accurate calendars, demonstrated the practical applications of astronomical knowledge in daily life. The major astronomical achievements of the Islamic Golden Age were characterized by a commitment to empirical observation, mathematical rigor, and intellectual curiosity. Islamic astronomers bridged the gap between the ancient Greek knowledge and modern scientific discoveries, leaving a lasting legacy that continues to shape our understanding of the cosmos. Their contributions exemplify the spirit of innovation and dedication to the pursuit of knowledge that defined this remarkable period in history. The legacy of the Islamic Golden Age in astronomy is profound and far-reaching. Islamic scholars' meticulous work during this period laid the groundwork for many of the astronomical principles and practices we rely on today. Their contributions have had a lasting impact, shaping modern astronomy and influencing scientific thought across various disciplines. One of the most significant legacies of the Islamic Golden Age is the preservation and expansion of ancient knowledge. Islamic scholars translated and preserved key astronomical texts from Greek, Indian, and Persian sources, ensuring that this valuable knowledge was not lost to history. By critically analyzing, improving, and expanding upon these texts, they created a rich intellectual environment that fostered innovation and discovery. This preservation of knowledge was crucial for later developments in astronomy during the Renaissance and the scientific revolution. The influence of Islamic astronomy extended to the realm of theoretical advancements as well. Islamic scholars challenged and refined the Ptolemaic model of the universe, introducing new concepts and corrections that improved its accuracy. The work of Ibn al-Shatir, who developed the Tusi Couple to explain planetary motion, was later used by Copernicus in his formulation of the heliocentric model. This connection highlights the direct influence of Islamic astronomical thought and development of modern scientific theories. Islamic astronomers also made significant contributions to the understanding of timekeeping and the calendar. Their work on the Islamic lunar calendar, based on precise observations of the moon's phases, provided a model for accurate time measurement. The development of accurate calendars and timekeeping methods was essential for religious, agricultural, and navigational purposes. These innovations continue to influence modern timekeeping systems and the study of celestial mechanics. The legacy of the Islamic Golden Age in astronomy is not just limited to the scientific advancements made during that period. It also encompasses the spirit of intellectual curiosity, critical analysis, and interdisciplinary scholarship that defined this remarkable era. The integration of knowledge from diverse cultures, the commitment to empirical observation, and the pursuit of mathematical precision set a standard for scientific inquiry that continues to inspire researchers today. In conclusion, the contributions of Islamic astronomers during the Islamic Golden Age were monumental in shaping our understanding of the cosmos. Their work in preserving and translating ancient texts, developing sophisticated astronomical instruments, and making groundbreaking discoveries has left an indelible mark on the field of astronomy. Scholars like Al-Fazari, Al-Battani, and Al-Khwarizmi exemplify the spirit of intellectual curiosity and innovation that defined this remarkable period. The meticulous observations and mathematical precision of Islamic astronomers laid the foundation for many of the principles and practices that modern astronomy relies on today. Their advancements in trigonometry, development of astronomical tables, and refinement of the Ptolemaic model significantly improved our understanding of celestial mechanics. The establishment of observatories provided dedicated spaces for systematic study and data collection, further advancing the field. The legacy of the Islamic Golden Age is not only found in the scientific advancements made during that time, but also in the approach to knowledge itself. Islamic scholars demonstrated the importance of cultural exchange, critical analysis, and interdisciplinary scholarship. Their willingness to engage with and build upon the knowledge of previous civilizations created a rich intellectual environment that fostered progress and discovery. As we reflect on the achievements of Islamic astronomers, we are reminded of the enduring power of knowledge and the importance of preserving and expanding upon the wisdom of the past. The contributions of the Islamic Golden Age continue to inspire and inform the study of the cosmos, highlighting the timeless value of intellectual curiosity and the pursuit of understanding. By appreciating the work of these pioneering scholars, we honor their legacy and recognize the profound impact they have had on the history of astronomy and science as a whole. The Islamic Golden Age serves as a testament to the remarkable achievements that can be made when cultures come together in the shared pursuit of knowledge and discovery. Thank you for watching. Keep looking up.